Okay, we're going to look at some different types of discontinuity, the first one being a jump discontinuity. For a jump discontinuity, both of the one-sided limits are going to exist. They're just not going to be equal to each other. So you can see the limit from the left is not the same height as the limit from the right. Both of the one-sided limits exist, they're just not equal to each other. And that's a jump discontinuity. Okay, in the middle box we have two types of removable discontinuities. Sometimes there's a point, like in the first example, and sometimes there's not. A removable discontinuity is when the limit exists, it's just not equal to the value of the function at that spot. If for the last example we have essential discontinuity, an essential discontinuity is when at least one of the one-sided limits does not exist. So if the limit was equal to infinity, that's the same thing as does not exist. So at least one of the one-sided limits does not exist. Another example could be an endpoint. For an endpoint, you have the limit from one side exists, but there's no graph on the other side. So again, at least one of the one-sided limits does not exist, and that's essential. Now the good news is for the AP test, they classify everything usually as just removable and non-removable. So the jump and essential kind of fall into the same category as far as the AP test is concerned. Okay, let's look at some of these examples of discontinuities. At the first spot, we're going to call this essential because it's an endpoint, and the limit as x goes to -8 from the left does not exist. So one of the one-sided limits does not exist. So that's essential. That's the same as non-removable. Okay, for the second one, we're calling this removable, and that's because we can just put that point back and it fixes it. So the limit exists as x goes to -6, and the function exists. They're just not equal to each other. So if we put this point back, it would become continuous. And that's an example of a removable discontinuity. Okay, when x is -4, we have a jump discontinuity. It jumps up. Notice that both of the one-sided limits exist. They're just not equal to each other. So that's a jump discontinuity. When x equals 2, we have an essential discontinuity because the limit as x goes to 2 is equal to -infinity, which is the same as does not exist. So for essential, we just need at least one of the one-sided limits to not exist. We have both of the one-sided limits, does not exist. Okay, when x is 5, we just have a hole in our graph. We would be able to fix that just by plugging in the hole. So we're going to say that this is a removable discontinuity. The reason we're calling this a removable discontinuity is because the limit as x goes to 5 of this function exists. It's just not equal to f of 5. And that's because f of 5 does not exist, not a point. There's no point when x is 5. Okay, the last one is just like the first one. It's an endpoint. So we're going to say essential discontinuity. But again, for the AP test, you would just say non-removable. Okay, for this example, we have a piecewise function. It's one thing to the left of 5. It's another thing to the right of 5. We can choose the value of k, and we want to choose something that makes these two functions connect when x is 5. So we have to decide what is the value of k. That'll just move it up and down. What is the value of k that would make these two functions connect? And so that would be continuous when x is 5. So the first thing we want to do is look at the limit as x goes to 5 from the left. So it's this function on the left, and if we were to plug in our 5, we would get 25 minus 3, and that's 22. The limit as x goes to 5 from the right is going to be 15 minus k. So now all we want to do is, in order to make sure that this limit exists, we want to set these two things equal to each other. We need 15 minus k to equal 22. And if you solve this, you get k is equal to -7. So now we can answer the question, what value of k would make this function continuous at x equals 5? It would be k equals -7. Okay, for this example, our function is going to equal to any constant k when x is 0. So that's just this point. And we can choose that value of k to be anything. When x is not 0, it's this function. So that means everywhere else it's going to be this function. Again, we're trying to find the value of k that makes this function continuous at x equals 0. You'll notice the limit from the left and the limit from the right are the same because it's the same function on the left, it's the same function on the right. The limit as x goes to 0 from the left or from the right is going to be e to the 0 plus 7. So that's 1 plus 7, so that's 8. So when x is 0, we just need k to equal 8. You let k equal 8, it fills in the hole, and becomes continuous. So now we can answer the question. If we let k equal 8, then this function will be continuous at x equals 0. Okay, this is similar to the previous one. It's just that it's a different function on the left side than it is on the right. So we're going to want to find out what the limit is for both of those as x goes to 3. Okay, for the first one, the limit as x goes to 3 is just going to be negative 12 plus 3. Okay, this is the function to the right of 3. So the limit as x goes to 3 from the right is just going to be 3 minus 12. Now we are getting the same value, so that means the limit as x goes to 3 is just going to equal negative 9. So that means when x is 3, it's going to also have to equal negative 9. So I'm going to have to set this equal to negative 9. Okay, after solving this equation, you get k is equal to 3, and that's going to be your answer. You have to let k equal 3 in order for this function to be continuous. You can always check your work. When you plug in a 3, you get 9 minus 18, which is negative 9. So you can make sure that it works. This one, you have to remember the definition of continuity at a point. So the limit as x goes to c of f of x has to equal f of c. We have two one-sided limits, so in order for the limit to exist, we need the limit from the left to equal the limit from the right. So we got to set those two equal. We can subtract 2t from both sides, and that's gone. We can subtract 2k from both sides, and add 6 to both sides. So now we know that k is equal to 1. Let me write that over here. It's given that f of c is 15, so we can put a 15 right here. And so we can set either of these limits equal to 15, doesn't matter which one. I'm going to remember that k is 1, so for the first one, I would have 3 times 1 plus 2 times t minus 6 equals 15. Remember, I already know what k is, so I just need to figure out what is t. So I can solve this equation for t, add 6 to both sides, subtract 3 from both sides. Divide both sides by 2. Now that I know that t is 9, I can write it up here at the top. T equals 9. I was supposed to find the value of k and t. So k is 1 and t is 9.